Okay, so we've seen several of these now that give this information at the beginning. The equation h equals h sub 0 plus v sub 0 t minus 16t squared gives the height in feet that an object is thrown in the air. In this equation, h sub 0 equals initial height, v sub 0 equals initial upward velocity. So that will be given to you because whenever it comes to like maybe the EOC that you'll see for this, they will not expect you to have that equation memorized if they give you a problem like this. They will either give you the equations with the numbers already filled in, or they'll give you this and you'll plug in that information, but you won't have to have that memorized, so I also will give you that equation on any of the problems that I ask you to do for me here. So, if a pumpkin is launched into the air from a height of 10 feet with an initial upward velocity of 32 feet per second, how many seconds does it take for the pumpkin to hit the ground? So the first thing we need to do for these is write our equation. Riley, what's our equation going to look like for this situation? Good. So if we want to find this, we're just going to have to type it into Desmos over here. So h of t is going to equal 10 plus 32t minus 16t squared. And you can zoom in and out. This one's pretty easy to zoom in and out. If you zoom out and it gets like super duper skinny, you can always go over here to the wrench and just adjust your y values. That will help if you do that. But this one you can see well enough. All you really have to be able to do is see that maximum point. Oh wait, no, not maximum. Yes. Oh, see about how many other people have the wrong notes. Does it say hit the ground? Yours is, yeah. Does anybody else have the wrong notes? If you got the wrong ones, it says like 1.9 seconds to hit the ground. Here. All right, let's see. They were mixed up.
I already gave you mine. You gave me one yesterday.
Okay. Did I give you two of the same one yesterday?
No, just one. And then
Okay, I got you. Okay. But I gave you another one today, which I did not. Needs to do. So everybody's is right now? Okay. All right. So we're going to type this in over here. I was about to say the answer is 26 because of what we were doing yesterday. Is that right? This question didn't ask how high the pumpkin went. Okay. What does this question ask? Hit the ground. Where's this pumpkin going to hit the ground? On that graph. Okay, what do we call this right here? What would we call that point? An x-intercept. You also could call it a 0 or a root, so 2.275. So 2.275 seconds. Okay, questions? All right, here's another one. Okay, we've got a same information at the top. A pebble is dropped off a bridge that is 120 feet tall. How long will it take for the pebble to hit the ground? So, for this one, this one's going to be a little bit different because it doesn't have two numbers like the last problem did. This 120, where should I put it in that equation? It is the h sub 0, right? It's the initial height, so I put 120 right here. What about that velocity? Okay, why is it going to be 0? It's just falling, it's just dropped, right? So they're not throwing it up into the air or anything, it's just dropped. So I've got 0 t, and then we'll have minus 16t squared. But really, do I need to write 0t? 0 times t is 0. It just goes away. So you can write it this way if you want 120 minus 16t squared. So if something is dropped, then that tells us that v sub 0 is 0 because we're not throwing it at all. Only gravity is making this fall. So if we go fix our equation for that. Now, so here's an example of what I was talking about earlier. If you zoom out, it gets really skinny, and you can still find the right point with this, but it's a lot harder to make sure you're at the right spot. So if you want to see the top of this, I would go to the y-axis and just make that number bigger. 100's not enough. Let's do 200. And really, you don't even have to see the maximum point here because it's not asking us for that, but I like to be able to see the whole thing. So this is asking us when we will hit the ground. Caitlin, where would we hit the ground here on this graph? Okay, what do we call that? The what? Specifically, we are going to look at the x-coordinates, but specifically we'll call that the x-intercept because it's where it crosses the x-axis. And you have 2, but the negative one doesn't make sense for this problem. So 2.739. So 2.739 seconds. Okay. Here, we don't have to write the equation. They give it to us, so we could just go ahead and put that straight over here. 60 plus 150t minus 16t squared. It gives the height in feet of a projectile that is shot from the top of a tower. How many seconds does it take for the projectile to hit the ground? So you can see here that we got a really high maximum here. Since it's not asking for the maximum, you don't really have to be able to see it, but I like to be able to see it, so if I make this like 500, let's see if that's enough. Yeah, that'll work. So that gives us our graph here. Ian, where will we look for the time that it takes to hit the ground for this one? On that graph, where would it be? On the right side? X-intercept, right? So x-intercept is 9.759. So 9.759 seconds. Okay, we are right here. Okay. All right, a soccer ball is kicked from the ground with an initial upward velocity of 42 feet per second. How long will it take for the ball to hit the ground? Here's another one that's still a little trickier because it's only got one number for this. So, Anna Grace, that 42, where are we going to put it in that equation? Okay, the v sub 0 right here, that's going to be 42. We got to put some number here for our initial height. What is that going to be? 0. How do we know? It started from the ground. If they just like left that information out, especially if they said something like a soccer ball is kicked from a tall building and the velocity is 42 feet per second, then you wouldn't really be able to answer that. But if it says from the ground, that tells you h sub 0 is 0. So for this, we'll have h of t equals 0 plus 42 t minus 16t squared. You can leave off the 0. You don't have to type that in. And we'll have 42t there. And so we can zoom back in some. We want to know where this hits the ground. We're looking at x-intercept. We got 2.625 for our time. And that is in seconds. Okay. Questions? Is that all on this one? It is, isn't it? Yeah. All right. So everybody's going to go over to Canvas. And you should see an assignment. This is going to be a quick assignment. We're going to do it real quick, and then we're going to go to the second part of the notes today. It's going to say projectile motion number 2. So I want everybody to go there, answer those questions just like yesterday. You're going to need Desmos so you can split screen that. Everybody know how to split screen? Okay, if you want to split screen, because this will help you, you have to minimize. So like if you're trying to split screen with Desmos, you got to minimize it. Then take whatever tab you want open, which is probably going to be your quiz tab, drag it over to this side and let go, and it'll make half of the screen one thing. And then if you click over here to the other thing that you want, it should make the other half of your screen that. And that way you don't have to constantly be switching back and forth. So just minimize, or not minimize, but what do you call it when you make it littler? I don't know. I don't know what that button's called. Whenever that button, what do you call that? This would be minimized if you make it go all the way down, right? I don't know what that's called. But anyway, you're going to do that and then just drag it over to the side. Height. We know if we're looking for maximum height, we're just going to look at that highest point. We've done hit the ground. Yes, we are. Thank you. Okay, here we go. Now, this is going to be the most difficult of the types of questions you're going to see for these problems. Because initial upward velocity is not easy to measure. If so, first of all, like let's say we want to measure the velocity of something or speed. Think of speed. What are we going to use to measure speed of something? What could we use? Like if I want to measure distance or height, if I want to measure height, I want to see how high this room is, I'm going to get a tape measure and I'm going to measure the height of the room. What have I got to have to measure velocity? What do you think? What? Speedometer? I'm not sure if that's like, well, a speedometer could work, like a speedometer could work if, like on a car or something, so we could have something on a car or possibly another apparatus, usually a car, that tells us speed, right? So it's measuring that, so that's one thing that we could use. What if we're just like observing it and we're trying to figure out how fast something is going?
I think it has something to do with that speed and acceleration.
No. No, we're trying to measure. Now we could find average speed of something, but that's not going to. We want instantaneous speed. We want the speed at a moment, right? So for example, if you drive from here to Winston and it's 50 miles and you do that in an hour, then your average speed was 50 miles an hour. You were probably not driving 50 miles an hour the whole time. You might have been driving 20. Hopefully, you were driving 25 out here on Elk Spur Street. But you were driving 70 on 77, right? So, but your average speed. But that, we want to know, like, your instantaneous speed, your speed at a moment. How can you measure that? Speedometer is one way we could do it. What else? What if it's like a ball? What do you have? Radar gun. Right? So you pretty much have to have a radar gun, first of all. We don't have... I wonder if the baseball team has a radar gun. But it's still not going to help us that much. Because you would have to have a radar gun. But the problem with a radar gun, for the problems that we're going to be looking at, is a radar gun is going to give you the speed of the object that you are looking at. But unless that object is going straight up into the air, so you have thrown this ball or this pumpkin or whatever straight up into the air, it still does not give you initial upward velocity. Okay? It gives you the total velocity, but it doesn't tell you the initial upward velocity, because most of the time when we're thinking about shooting something, particularly with our pumpkins that we're going to shoot, what's going to happen is we're going to shoot the pumpkin, and it's going to go up in the air like this, and then come back down, right? So what happens whenever you shoot that pumpkin is you're shooting it in a direction that is neither straight up nor straight out, right? So you guys have not had physics and probably do not know much about vectors, but what this would be your vector here that would tell you about that velocity of the pumpkin. It is made up of two parts. It is partially going up and partially going out, right? So this would be your horizontal velocity, and this green part right here, that's your initial upward velocity. So even if you have a radar gun, you still can't really measure initial upward velocity unless you're shooting something straight into the air. If you're shooting something straight into the air, the velocity is the initial upward velocity because it's only going in one direction. But if it's going sideways a little bit, even just a little, then the initial upward velocity is not the same. So even if we had a radar gun, even if we borrowed a radar gun from the baseball team, we're not going to be able to see how fast our initial upward velocity of our pumpkins, unless we shoot them straight into the air. And if your pumpkin gets shot straight into the air, it's not going to travel 5 feet, and you are not going to get counted as having a working catapult, right? Because our point is to shoot it further away. So there is another way that we can find initial upward velocity, and this is what we're going to do whenever we do our experiment with our catapults. Okay. So what we can do is, while we can't find initial upward velocity, we can find all the other parts of this equation, right? So we can find all the other variables, leaving us just initial upward velocity, and then we can solve for that. So here's an example where that is going to happen. We have a rock is thrown from a bridge that is 32 feet tall. It takes the rock 1.9 seconds to hit the ground. What is the initial upward velocity of the rock? So we don't know what the initial upward velocity is. It's what we're trying to solve for, which means we've got all these variables. We've got h of t, we've got h sub 0 plus v sub 0 t minus 16t squared. What we want to do is we want to replace all of the variables except for v sub 0. So, somebody tell me a variable that I can replace. Evan?
All the time. T.
Okay. Time, what can I replace the time with? 1.9, right? So, time here is going to be 1.9 seconds. So, I'm going to have, plus remember v sub 0 is going to stay here. We're not doing anything with it. This t right here is going to be 1.9, and then this t right here is also going to be 1.9. Okay, that takes care of my t's. I still have, though, the h sub 0 and the h of t over here that I need to replace. 32 for my h of 0, right, because initial height is just that height of the bridge that it's thrown from. So that's 32. So we're going to put 32 right here. What about the h of t over on the other side? Now numbers, right? The problem doesn't have numbers in it anymore. Okay? It's not always 0. But there is a phrase here that tells us it's going to be 0. What's happening at this 1.9 seconds? It hits the ground, right? So even though that's not a number, we know that if something hits the ground, that tells us that the height, and the height, don't let it confuse you like that h of t is like a sort of like a y. You could use just the h if you wanted to. It tells us that height is 0. So we're going to put 0 right here. So if we can figure out how long it takes something to hit the ground, which is much easier to find than having, I mean, there's probably something that will tell you initial upward velocity, like I imagine NASA or the military or somebody somewhere's got something that will just like scan it and tell you initial upward velocity, but it's not going to be easy to come by, and it's not going to be cheap, right, if you have that. But really you just need a timer to see how long it takes to hit the ground. We could find that very easily. So now we've got all of our variables are filled in except for v sub 0, so we can solve for that. So somebody tell me what you think we should do to try to get that v sub 0 by itself. Okay, I can subtract 32. That'll be good. While I'm doing that, I don't like v sub 0 times 1.9 because we usually put the number first in the variable, so I'm going to write it this way, 1.9 times v sub 0. And all of this stuff, 16 times 1.9 squared, that doesn't have any variables in it, right? So is it okay if I just type that into the calculator right now and get a number? So 16 times 1.9 squared is going to give us 57.76. Okay, this is starting to look more manageable, less scary. All right, Giancarlo, what would I do next? Good. Add the 57.76. And so negative 32 plus that 57.76 is going to give us 25.76. Okay. And then, Evan, what's the last thing I'm going to do?
Divide everything by 1.9.
Okay, divide by 1.9. And so if I divide this number right here by 1.9, I have 13.558. And that will be feet per second for our v sub 0. So initial upward velocity, unless it gives you an equation. If it gives you an equation, if you've got h of t equals 10 plus 30t minus 16t squared, initial upward velocity, all you got to do is say it's 30. Just pull it from the equation. You had some of those the other day. But if it does not give you the equation, you're going to have to go through this and solve this. So this one's going to be the most difficult because you can't just type it into Desmos and find the answer for those. For initial upward velocity. Okay, questions? Okay, so we have, again, similar thing happening here. So, I'm trying to make it all fit, and it's okay. All right, so same information. A kickball is kicked from the ground. It takes 2.7 seconds to hit the ground. What is the initial upward velocity of the ball? So again, very similar thing that we're doing here. We need to plug in values for all of our variables except for v sub 0. Okay, so we got 8 again, h of t equals h sub 0 plus v sub 0 t minus 16t squared. We're not going to put anything here for our v sub 0. Riley, what's one number that I could plug in? Okay, where's it going to go? T. All right, so I will have the v sub 0 I know I'm going to leave. I'll have 2.7 minus 16 times 2.7 squared. So that takes care of the t. All right. Who can tell me another number I can plug in? Aiden? Okay, where's it go? H of t or h sub 0? Okay. All right, how do we know? Right, from the ground tells me that that h sub 0 equals 0, right? So very good. Okay. All right, Evan?
Also 0 for A.
Also 0 for h of t. How do we know that?
Because it hit the ground.
Hit the ground, when you hit the ground, height is also going to be 0. So we put a 0 really in both places there. All right, so I've got 0, that 0 right there I don't really need, right? So I'm going to rewrite this. I don't like 2.7 to be on the back side of that variable there, so I'm going to do 2.7 v sub 0. And just like the last time, I'm just going to type that into the calculator. 16 times 2.7 squared. And I'm going to get minus 116.64. Okay, Anya, what am I going to do to solve that? Okay, good. Okay, and last thing, Anya? Good. And so if we divide that by 2.7, we will get 43.2. So 43.2 feet per second is our v sub 0 there. Okay, questions? All right, this one is more difficult. All right, a volleyball is hit into the air from an initial height of 9 feet. It takes the ball 8 seconds to hit the ground. What was the maximum height that the ball reached? So, this question wants to know maximum height. What have you got to have before you can find maximum height? You've got to have velocity, because you need to know this equation to type it into Desmos, right? Or you could do axis of symmetry if you want, but if problems like this are going to have to be calculator active anyway, so Desmos is easier. So for this, we need to know this equation. It gives us h sub 0, but it does not give us v sub 0, right? It doesn't tell us initial upward velocity. So what we're going to have to do on this problem, it doesn't tell us that we have to find v sub 0, but we're going to have to find v sub 0 before we can answer the question that it's asking. Okay? These can be tricky because it doesn't explicitly ask you to find initial upward velocity. But we need to find that first. So we're going to have, again, the equation. So looking at the information we have, we know we don't have the initial upward velocity. That's what we're trying to find. Kama, what is a number that we could plug into this? Okay, 0.8, where's it going to go? T. Good. So we're going to have v sub 0, time is going to be 0.8 minus 16 times 0.8 squared. All right, Haley, give me another number I can plug into this equation and tell me where it should go. Okay, where's 9 going to go? Which h? H sub 0. All right, that's our initial height. That goes right here. Great. Okay, so we've got almost everything. Savannah, what's going to go for our h of t? 0. Right here. Because we are going to hit the ground, right? Okay, so this is just like the last problem. Rosalind, what should I do first to solve that equation? Okay? And also, like, you don't necessarily have to move the 9 first. You could, like, combine some like terms if you wanted to, but I think it's helpful to move the 9 and go ahead and get it on that side. It makes it seem a little easier to solve. So we got 0.8 v sub 0. We got 16 times 0.8 squared is going to give us 10.24. Okay. Ian, what would I do next? Yes. So that's going to give us 1.24, 0.8 v sub 0. Blakeland, what's the last thing we're going to do? Good. Alright, so 1.24 divided by 0.8 is 1.55. So v sub 0 is 1.55 feet per second. It feels like we're done. Is that the answer to the question? No. Because we did all that work, but we're still not done because it didn't ask us for initial upward velocity. It asked us for the maximum height. So what we're going to do now is we're going to plug this into the equation. But we want to do like we've done the other problems. We need the t to still be in the equation. If you plug in that 0.8 for the t, you will not get anything whenever you do this. So you're going to have h of t equals 9 plus 1.55 t minus 16 t squared. Okay, you still need the t in the equation because 0.8 is not always the time. It's just the time when it hits the ground. We needed this to be the time for any time because we need to find the maximum height, which is not going to be when it hits the ground. So if we flip over here to Desmos and type this in, we got 9 plus 1.55 t minus 16t squared. Oops, not like that. Oops, still not like that. All right. And if we look at this, be careful. You might want to zoom in a little bit here because the y-intercept and the actual maximum height are really, really close. Really close, right? So on this particular problem, we're asked for maximum height. So that's going to be this point right here. And it's going to be at 9.038. So our maximum height is going to be at 9.038 feet. 1.55 feet per second is a barely nudging something in the upward direction there. Oh, sorry, excuse me. All right, questions? All right. Okay, so I'm going to walk you through what we're actually going to do on the catapult experiment. So it'll so you'll have seen it before, and I'll help you with it when we get there too. So the first thing that you will have to do for your catapult is you're going to have to measure the height from the ground to the place where your projectile sits when it will be launched. Okay? So, should we actually shoot one of them? Yes. Okay, let's use one of the small ones. Let's go. I don't think it shoots too awful hard, so we won't knock out a window. Okay. So, we need a helper. Be my helper. So we'll shoot something flex. Come on over here. a difference in how far it'll go. It'll go further if it's up high. So they're all going to be sitting on the ground. So, now I'm going to measure this here. This is going to be about where the pumpkin launches. It looks like it's about 5 inches right there. So I'm going to record that. I'm going to actually record this right here, because if it's only 5 inches, then we are going to have to convert. All right. So let's see. Here's your ammo. All right. We're going to set the. Where's the best? Maybe right here. You guys can see okay if we do it right here. So we're going to set it on the ground there because we've got to measure. And then I need to get my timer. Okay. All right. So you can load the pumpkin there. All right. All right. So I'm going to tell you to go, and then I'll time it. All right. On your mark, get set, go. All right. That time I got 1.34. We're going to do it 3 times and take an average because it's not the most accurate. All right. Let's try it again. All right. All right. On your mark, get set. Okay. You ready? All right. On your mark, get set, go.
Much higher.
That went. This is crazy. I got 1.34 again.
Oh.
What's the likelihood I could, like, if I try? Got 1.51 trying to stop it at 1.34 that time. All right, let's do it one more time. All right, you ready? On your mark, get set, go. I got 0.98 that time. All right, so now that you can tell, I may actually go 1.34 since I got it twice that time. Feels like it's just meant to be. Thank you so much for your assistance there. All right, so that's what you're going to do with your pumpkins. And that one's been cracked. I'll retire it. So you can tell there was some variation because we are not shooting very precise machines here. So that second time it went a little higher than the other 2 times, but we're going to kind of go on an average. This is not going to be like ballistics level, analysis, but we will do this. You need to go. The projectile motion number 3 is going to be the assignment, so if you'll do that from home, that'll be good. All right, so 5 inches. I need this to be in feet. If I put a 5 into this equation, it thinks it's feet. So if it's only 5 inches off the ground and I tell my equation it's 5 feet off the ground, you'll be terribly off. All right. So how do I change 5 inches to feet? Divide by 12. So 5 divided by 12 is going to give me 0.416 repeating. So 0.416 repeating. It must be in feet. All right, we're going to launch the catapult. We did that. We're going to go with 1.34 since I did get that number twice. All right, then we need to use our formula to find initial upward velocity. So h of t equals h sub 0 plus v sub 0 t minus 16 t squared. We're trying to find initial upward velocity, so that's what we're not going to put anything there. Let's see, Giancarlo, give me a number I can plug into this equation. What? The 1.34, where would it go? T. All right, so I'm going to have v sub 0 times 1.34 minus 16 times 1.34 squared. Okay. Let's see. Anna Grace, what's another number I could plug in here? Good. That 0.416 repeating is my initial height. And then at 1.34, my pumpkin hits the ground, which means this height over here is going to be 0. Okay, so I'm going to solve this. Lexi, what would I do first to solve this? So I'll get negative 0.416 repeating equals, I'm going to write this as 1.34 times v sub 0 minus, let's type that into the calculator here, 16 times 1.34 squared is going to give me 28.7296. Okay. All right. Then from there, Haley, what do I need to do? Good. When you do this, to type in that 0.416 repeating, just put a bunch of sixes there. It'll be close enough. 28.31293 repeating. 1.34 v sub 0, and then we'll have to divide by that 1.34. So divide by 1.34. And so we get 21 point, we'll do 3 decimal places here, 21.129. Oops. So my initial upward velocity is 21.129 feet per second for that particular one. Any questions on that? All right, and then what we're going to do in our experiment is we're going to see if we can find what the initial height was and see if it's reasonable, right? Because we kind of saw how high that second one at least went. And we'll see if it's a reasonable answer. They may be a little unreasonable because without a really precise way of timing exactly, we might be a little bit off. So h of t is going to be 0.416 repeating plus 21.129t minus 16t squared. This question only asks us for the equation, so that's all it's asking for here. And then when it asks for maximum height, we're just going to type that into Desmos. So we'll have 0.416 repeating plus 21.129t. And so we can see here our maximum height, 7.392 is what we're getting. 7.392 feet. Maybe for that second one, I don't know if that was too far off. I don't think it went quite 7 feet. Maybe more like 6, but kind of close. The further your catapult will shoot, or the higher in the air, the distance doesn't really matter, but most of the ones that shoot further also shoot higher, the easier it is to get a little bit more accurate of a estimate, because it's in the air longer and timing it is a little bit easier to do. If you make one that's really bad, that one that we just shot was not great. It barely shot 5 feet. If you make one that's not great, you can still make 100. It's fine. Your results may just be a little less accurate whenever we do the experiment. Okay, questions? All right, we got 17 minutes. You have projectile motion number 3 that you're going to do for me. You're going to either need, you probably have room on the back of those notes if you want to use that, or whiteboard if you would like to work out those problems, because for initial upward velocity on most of these, you're going to have to actually, do some writing out of the equations. So go ahead and